Are you people getting into McGill? No? You go into work to McGill, or are you blocked by the strike? No trouble going through?
Yeah, they're not doing that stuff.
Okay, before getting more into solution theory, but I wanted to do one last thing so I can give you some problems to do. When phase diagrams are calculated using FactSage, the machine does it all for you, and it's done by the technique of Gibbs energy minimization, where I said that you have the common tangent line here. Common tangent line gives you the phases at equilibrium by minimizing the total Gibbs energy, but it's also exactly the same thing as saying the common tangent construction also gives you the chemical potentials being the same in the two phases at equilibrium. Okay, so I'm going to give you in section 13 for homework to play with, because I think it's important to do a few calculations by hand with your calculators and so on. It gives you a better appreciation for what's happening in the phase diagram sometime than when it's all done by the machine. And to do that, I want to, but you can't actually minimize the total Gibbs energy when you're doing things by hand, but you can set your activities equal, at least for some simple examples. So I'm going to give you a couple of equations. Okay, I'm just with respect to this germanium silicon diagram, you have the two phases at equilibrium, meaning if you say extrapolate these lines to either end, this gives you the chemical potential of germanium, and the intercept over here is the chemical potential of silicon, and the two of them are equal, as was shown here on page 41. The chemical potential of germanium in the liquid is equal to the chemical potential of germanium in the solid, and the same thing for silicon. That's your criterion for equilibrium. So let's use these equations. Setting these equal is the same thing as minimizing the total Gibbs energy, but let's look at it this way. We already did this. I subtracted the Gibbs energy of fusion from this equation. I subtracted the Gibbs energy of fusion of pure germanium, Gibbs energy of fusion of pure germanium, the difference between that from each side. I already did this. So you subtract this from each side of this equation, rearrange things this way, and what you get is the chemical potential of germanium in the liquid minus the relative to the chemical potential of pure germanium liquid at the same temperature, and the same thing here equals the Gibbs energy of fusion. It ends up with this. This is the delta mu of germanium in the liquid, which is RT log activity of germanium in the liquid. This is delta mu of germanium in the solid, which is RT log activity of germanium in the solid, equals minus the Gibbs energy of fusion of germanium. So this is just another way of writing out this equation, but it makes it a useful form to do your calculations. So this is telling you, so then I already asked the question, I said, well, this then is the activity of germanium on the liquidus, this is the activity of germanium on the solidus, okay, when the system's at equilibrium, and that's minus the Gibbs energy of fusion of germanium at the temperature in question. And I said, but wait a minute, when you have two phases in equilibrium, shouldn't they have the same activity? So the only way these two activities could be equal would be if this delta G of fusion was always zero, which it isn't. And the answer was, well, these are activities are only, its chemical potentials are always equal when two phases are equal in equilibrium, but your activity is with respect to a standard state. So this is the activity of liquid with respect to pure liquid standard state. This is the activity of solid with respect to pure solid standard state. And of course you have the right hand side, which is simply the change of standard state. So you have this equation, and then you have a very similar equation that's replacing germanium by silicon, which you get from here, and you get the same thing. Okay, so you have this equation, and if you want to solve the thing by hand, then these are the two equations that you have to simultaneously solve. Okay, so let's just give you an example. And I think it's useful to look at it this way too, because it gives you a little better idea sometimes of what's going on. So let's go back to the phase diagram. And I'm going to try to calculate these 2 points. What I'm going to try to do in the germanium silicon system, I'm going to calculate the composition P2 and Q2 at 1100 degrees. And I'm going to assume ideal liquid and solid solutions for the moment, which isn't the case, but let's assume they're ideal liquid and solid solutions. So what we have here is I have to give you some data now. We have the melting point. The melting point of germanium is 938 degrees Celsius, which is equal to 1211 Kelvin. the melting point of silicon is 1114 Celsius. No, 14. Let's think 14. 14. Which is 1687 Kelvin. And we got to get the Gibbs energy of fusion. We need to choose those equations. We need the Gibbs energy of fusion. Okay, so in general, the Gibbs energy of fusion, you need the heat of fusion at the melting point, and you need the CP of the solid. You need the CP of the liquid. I'm going to make an approximation. I'm going to say CP of the solid is approximately equal to CP of the liquid. This is just to do rough. The point of this is to have you play around, not to do exact calculations. This simplifies life. And in that case, the Gibbs energy of fusion is equal to the heat of fusion minus the temperature delta G T delta S of fusion. Okay, where now if the CP liquid equals CP solid, the heat and entropy of fusion are temperature independent. Okay, so in that case, and delta G naught of fusion equals 0 at T equals T naught fusion. When the temperature is equal to the melting point, the Gibbs energy is equal to the melting point. Okay, and so from that I can get that the heat of fusion equals temperature of fusion times the entropy of fusion. That strictly only applies at the melting point, but if the CP liquid is equal to CP solid, then that applies everywhere because the heat and entropy are temperature independent. Alright, so I can put this equation back into here, and what I'm going to get is that the Gibbs energy of fusion is equal to the heat of fusion times 1 minus T over T naught fusion. When T equals T of fusion, the Gibbs energy of fusion is 0. When T is greater than T fusion, the Gibbs energy of fusion is negative, and the liquid is more stable than the solid is positive the other way around. Okay, this is just making this up. This is only true if, in fact, this equation is linear with T, which means the heat and entropy are independent. So this is an approximation, but you don't do this when you're doing a real calculation, but it's not that far off, and I want you to be doing a whole lot of mathematics. I want you to get the... Okay. So, now we have the heat of fusion, so the heat of fusion of germanium equals then the heat of fusion of silicon. So the heat of fusion of germanium equals 36,945 joules per mole, and of silicon it's 50,200 joules per mole. You can put those back into here along with the melting points, and you get an expression for the Gibbs energy of fusion as a function of temperature. I might as well write that over here. So the Gibbs energy of fusion of germanium then is then simply 36,945 times 1 minus T over 1211, and the Gibbs energy of fusion of silicon is 50,200 times 1 minus T over. Okay, so that gives me my Gibbs energy of fusion. Okay, so now I can go back into these. Okay, so those are my two equations which I need. I needed the Gibbs energy of fusion. I've made the assumption that the CP liquid equals CP solid. This is not necessary, of course. The heat of fusion is the heat of fusion at the melting point plus the integral of CP dt, and you can get CP, you can get the whole thing. You don't have to assume the heat of fusion and temperature of fusion are independent of. You don't have to assume CP solid equals CP liquid to do the calculations. That's good. Okay, so now we have the two equations, RT log activity of germanium on the liquidus minus RT log activity of germanium on the solidus equals minus the Gibbs energy of fusion of germanium, which can be used, that equation there. The RT log activity is given by RT log mole fraction of germanium on the liquidus plus RT log gamma of germanium on the liquidus. Okay, if it's not an ideal solution, minus RT log mole fraction of germanium on the solidus plus RT log gamma of germanium on the solidus. This is the activity coefficient of the liquid on the liquidus. This is the activity coefficient of the solid germanium on the solidus. Okay, and that's equal to minus 36945, 1 minus T over to 11. Okay. And now we have a similar equation for the silicon, RT log mole fraction of silicon on the liquidus, etc. Exactly the same sort of thing. Okay, so you have the two equations which you now have to solve. Okay, so these equations are, you have two equations, you have three unknowns. Well, three unknowns, okay. You have your activity coefficients, of course, are unknown, but your activity coefficients are functions of composition. So in actual fact, you could, for example, assume a regular solution, in which case RT log gamma of germanium would be equal to mole fraction of silicon squared times the constant. Okay, so these are, in principle, the RT log gammas are functions of temperature and composition. Okay, so I have two equations. What I can do is I can choose a temperature, 1100 Celsius, and then that eliminates one variable. Now I have two equations and two unknowns, the two compositions. I can solve for the compositions P2 and Q2. Okay, this becomes very complicated, of course, the minute these RT log gammas are not zero, because then you have a complex sort of equation, but that's how you would do it. The RT log gamma, which is the excess gives energy, partial excess gives energy, could be expressed as your power series in your normal polynomial or something, and then you'd have to solve these two polynomial equations with an x mole fraction. You could solve them numerically. That's how you do it. That's not the way FactSage does it. FactSage minimizes the total gives energy, but it's mathematically exactly the same thing. But let's just, for fun, assume, okay, so that's the general equations you have to solve. Let's make the assumption, as I said, I'm trying to calculate at 1100 degrees. I'm trying to calculate assuming ideal solutions. So if I assume ideal solutions, I can remove the RT log gamma term. Okay, so now I have RT log mole fraction of germanium in the liquid. That is the composition on the liquidus. Minus RT log germanium on the solidus equals this. And my equation for silicon would be RT log mole fraction of silicon on the liquidus. Again, assuming an ideal solution, mole fraction of silicon on the solidus equals minus whatever, 50,200, 1 minus T over 1687. So this is assuming ideal solutions. You can take out the RT log gamma terms. Now these are actually quite simple to solve. You choose a, remember X, and of course, X silicon on the liquidus is 1 minus X germanium on the liquidus, and the same thing for the solidus. All right, so solve the two equations, and if you think about it a bit, you can do it by, you're actually solving for log X in the two cases, so you can work it out as two linear equations, really. So you pick T. You pick T is to be 1373 Kelvin. Put that into these two equations. You get then two equations and two unknowns: X solidus, X liquidus, and solve the two equations. Okay, I won't do that for you, but it's very easy to do. Think about it. And what I get is I get X. My solution, if you want to work the thing out for yourself, was that X germanium in the liquidus, X germanium on the liquidus was equal to X silicon, and X silicon on the liquidus was 0.21, and X silicon on the solidus was 0.49. That's assuming an ideal solution. If you want to do it yourself, and of course 0.21 is over here and 0.49 is over here, so it's not too bad. It's going from maybe here over to here. The actual thing is just the whole tie line, the real tie line is displaced a bit to the left, which would indicate that the solid is a bit more stable than we thought relatively. Okay, but now if you then had a regular solution, then you'd have two parameters. This would be omega liquid times X silicon squared liquid. This would be omega solid times X silicon squared solid. The same thing here. Okay, so you can play around a little bit with these things, but this is what's going on. Okay, so that's another way of looking at the Gibbs energy minimization. You can maybe see a little bit more now what's happening. What happens if I increase RT log? Even though when you're doing an optimization, even though you're not solving it this way, you can think of these are the equations that are being solved. Okay? And then, in principle, at least. And so you can see what would happen as this term gets more positive, what happens as this term gets more negative. It gives you an idea of what. Okay, rather than just minimizing the Gibbs energy, it's hard to visualize what's happening. Okay, this makes this, if this positive deviations over here are going to make this term more positive. What's that going to do to you? How's it going to shift things? Gives you an idea. All right, it pays to look at things in more than one way, and just as you no longer anybody ever does long multiplication anymore with the paper and pencil, you always use your calculator. It's still worthwhile to understand how to do it, otherwise you don't quite understand what's happening, and that's why they still teach children their multiplication tables and to do the whole thing out by hand, even though they know that they're going to be using hand calculators or computers in the future. And I think it's sort of the same thing here. I'm not saying you shouldn't use FactSage, but you should be able to understand how to do it by hand, at least in principle, at least to set up the equations, and then let somebody solve it. So it's kind of equivalent. Let's do another example, because I think this is useful. Let's do the... Okay, so you always have the two equations to solve. These two equations that I showed you, RT log activity on the liquidus minus RT log activity in the solidus is minus the Gibbs energy of fusion. Of course, I don't have to say it. If this is solid alpha and this is solid beta, then it's the same equations, except that now it's the delta G of phase transformation rather than the delta G. Or even liquid and gas, whatever. It's the same principle. Let's take a system in which we have this also shows you these equations work two ways. You can have, if you have the thermodynamic properties of the two phases as we did here, assuming you did, then you can calculate the phase diagram. But of course the phase diagram gives you information on the thermodynamic properties as well. Okay, since if we have the phase diagram, then you put it back into these two equations. For example, if I had these two equations, I shouldn't have rubbed them off. Suppose I had these two equations and I have the phase diagram, and I assume the liquid is I should have written these. I have the two equations. I have one, there's the mole fraction of the liquidus, there's the mole fraction of the solidus, and let's say we have the chemical, we have a interaction parameter, a regular solution interaction parameter for the liquid, and a regular solution interaction parameter for the solid. So you have your RT log gamma terms can be calculated. So I say if you know what these are, you can then calculate the phase diagram. But if you have the phase diagram, now you know what the x's are. Okay, so you can go back and you can calculate your two omegas. So your phase diagram goes, you can use the equations the other way. And of course you're assuming that both are regular solutions. Maybe that's not a good assumption, but if both of them are regular solutions, then the same equations permit you to go and solve the thing backwards. You have these four parameters at a given temperature. If you know these two parameters, you can get these two, but if you know these two, you can get these two. Or you might assume that the liquid was ideal. So in other words, this one was 0. And now for the solid, I could use two terms. I could have XAXB times A plus BX or something. So I got two equations basically. I got the activity. This is the other thing to think of when you look at it this way, is how many equations do I have? You cannot, if your number of equations equals your number of variables, then you can get an exact solution in principle. Okay, so if I'm assuming that the liquid and the solid are both regular solutions, then I have two equations, as given the phase diagram, I have two equations and two unknowns. Okay, or I could assume I could use a subregular solution where this was a function of linear function of composition or something, but then I would have to assume something about this one. Or I'd assume that this was temperature dependent, or okay, how are you going to... Okay, but what you really have at any temperature, you have the chemical potentials of the two phases are equal, so you have two equations at each temperature. Think in terms of the number of... Okay, I'm going to give you another example now of better. Let's take a system that is simpler. I'm going to take, and I don't have this on the diagrams, I'm going to actually draw a simpler case. This is the gold silicon phase diagram, temperature composition diagram. And this diagram is a simple eutectic system, no solid solubility. And at mole fraction of silicon equals 0.81, the liquidus temperature has been measured as 1523 Kelvin. And of course here the melting point is 1685 Kelvin. It's the same silicon, it's the same silicon as over here, so the Gibbs energy diffusion of silicon is still equal to that. Okay. Now I can write out then RT log activity of silicon on the liquidus minus RT log activity of silicon on the solidus equals minus the Gibbs energy of fusion of silicon, which is minus 50,200, 1 minus T over 1687. And now RT log activity, this is equal to RT log of X silicon on the liquidus plus RT log gamma of silicon on the liquidus minus RT log, I'm not going to expand this one, silicon on the solidus equals minus 50,200 and minus T over 1687. Okay. Now from the phase diagram, we see that the silicon solid is almost pure. Okay, so it's almost pure solid. That's the phase diagram shows negligible solid solubility. In that case, the activity of silicon in the solid phase is equal to 1. So this term drops out. Okay, so activity of silicon in the solid equals 1 because the liquid's in equilibrium. The solidus comes down here vertically. Everybody happy? Now the mole, so then if I take this equation and I substitute in T equals 1523 Kelvin, and I substitute in X silicon on the liquidus is 0.81, I can solve this equation. Now I've got the X and I've got the T, so I solve this equation and I end up with the gamma silicon on the liquidus equals 0.95. Or I'll just finish it up over here, that G excess of silicon on the liquid is RT log gamma silicon on the liquidus is minus 670 joules. Okay, so now, okay, everybody understand that? So now, yeah.
Professor, if the temperature is at eutectic temperature, so the solid solution is at eutectic point, so what will be the assumptions?
I don't get that.
If the temperature is at eutectic temperature and
Yeah.
the solid solution is at eutectic point,
Then if you do the same thing, you'd be calculating the gamma silicon in the liquid at the eutectic point.
and the activity of the silicon will be
Be 1 in the solid.
one solid.
That's with respect to the solid standard state. It's not 1 in the liquid standard state. This is the activity with respect to the solid standard state, right? Mu minus mu naught solid. This activity is mu minus mu naught liquid. Yeah, at the eutectic point. Well, anywhere along here in the equilibrium, the activity of silicon in the solid is equal to 1 with respect to pure silicon. Solid, because it is pure silicon solid. But the activity of silicon in the liquid is not equal to 1. It's more pretty close to an ideal solution, so it's going to be pretty close to the eutectic. Okay, so now what's important here then is to, first of all, remember I said there are two equations. First of all, what I've done with this equation now is I've actually solved for gamma silicon. I gave the example before with the germanium silicon diagram. Okay, and from the phase diagram you can't unless you make some assumption. You can't actually calculate the two gammas because you got two equations, two unknowns. But here, you've only got one equation. I did not use this, there's an equivalent expression for RT log activity germanium, but I didn't need it. Okay. I only used the one expression for silicon, for the solvent silicon, because I know, basically, I know the activity in the solid phase is equal to 1. Okay, so if you have very little solid, if you have solid solubility or very little solid solubility, then the phase diagram actually gives you the activity coefficient on the liquid. It's exactly, there's no modeling here. I'm not assuming a regular solution or anything, I'm just calculating down the liquid. And I'm calculating the excess Gibbs energy, then, or the same thing. Okay, so that's why when you have very little solid solubility, you see it's really only, and the important thing then is, and this can be lost, is again, for calculating the phase diagram, okay, the only thing I need to calculate this liquid, if the liquid here, this is important and it's missed when you're using the computer. It's missed a lot by CalFed people too. The solid is pure, or close to being pure, so the activity of the silicon is 1. This liquid is that you're going now the other way. Let's say I know gamma. I know the activity coefficient of silicon in the liquid as a function of composition. If I know the activity of silicon in the liquid as a function of composition and temperature, I can calculate the liquids. I don't need the activity coefficient of germanium. All I need is the activity coefficient of silicon. Or going the other way, this liquid is here will give me exactly the activity coefficient of, maybe I should be putting it this way. If I analyze the phase diagram has been measured. I see that the phase diagram has no solid solubility over here and over here. Okay, so I calculate the activity coefficient of silicon in the liquid. Okay. The phase diagram, however, gives me no information whatsoever about the activity coefficient of germanium in the liquid, along this liquidus. But when I do a model, what I will do is, when you're using an optimization, you don't just calculate gamma point by point. What you do is you come up with some sort of a model. RT gamma is a regular solution model or something. Let me show you what I mean. So you have the regular solution model. So let's assume the GXS liquid is X1, X2 times omega. Okay, and then so I fit this up to, I can, from the values, from the given value, from the various values of GXS of the gamma silicon along here, GXS of silicon along that line, I would have GXS of silicon equals X gold squared times omega. That's your parabolic thing. And I would probably find a pretty good fit for omega. Okay, so fine, I fitted up my phase diagram to this regular solution equation. And then you write GXS of gold then is equal to X silicon squared times omega, because that's your regular solution equation. Okay, and then you go and get your GXS of gold, but you really haven't. Okay, because all you've got is the GXS of silicon. It's your model that's gone back and given you GXS of gold, but there's no real reason to assume that that's going to be exactly right. Now we can talk about that more later. Yes, there is some reason, I mean clearly, but it has to do with endpoints of integration and so on, but I'm introducing something I'll talk about next week. But you see that the actual information that the phase diagram is giving you is not the Gibbs excess Gibbs energy of gold, it's giving you the excess Gibbs energy of silicon, period. You're not getting both, you're getting one. But when you optimize this thing up, you can fool yourself into thinking you got the GXS of gold, but you really don't, and it has to do with endpoints and so on. Now the GXS on this liquidus is the same thing. All along this liquidus I use the other equation with gold, and I'll get the excess Gibbs energy of gold along that line. Okay, so I get the excess Gibbs energy of gold from here to here, and I get the excess Gibbs energy of silicon from here to here. I have one point at which I'm going to have both. And I can use that as the endpoint of my Gibbs-Duhem integration, and I'll talk about that next week. But you got to, this is just to lead up to it, to show you what information you're getting. And really this liquidus gives you the excess Gibbs energy of the liquid, of silicon. This liquidus gives you the excess Gibbs energy of gold. You don't get both. So be careful that you realize, even if the computer spews out both, then you have to decide how did the computer get the excess Gibbs energy of gold, because it didn't, I didn't input that. All right? You see what I'm... And that's why doing this kind of thing is kind of a useful exercise. Okay, when I talk about the Gibbs-Doom equation next week, you'll see exactly how it works and what assumptions the computer is making. And this is perfectly fine. This is probably a reasonable way to do it, but you got to be careful. I'll show you what. And you got to understand what the actual thermodynamics of it, rather than just trusting the machine, which can make assumptions. Or another way, the machine will make assumptions, and you're not aware of the assumptions that are being made. You must be aware of what assumptions are being made. Okay, by the way, if the solution, so GXS, if the solution were ideal, would the liquidus be higher or lower?
Solution, sir.
Higher, yeah. The excess Gibbs energy is negative, so the liquid is stabilized. Okay, so if it were ideal, it would be a little bit higher. Okay, the other thing in terms of the other equation is that, remember too, that what the phase diagram is giving you the excess Gibbs energy or chemical potential along this non-isothermal line. It is not giving you the enthalpy and the entropy. Okay, let's suppose then that I decided that and again, you have to realize that seeing what's going on here can get you not thinking about the thermodynamics. The computer can give you stuff that doesn't really mean much. So what I do is say I have the phase diagram, the liquidus was been measured, and so everywhere along the liquidus I can get G excess silicon along the liquidus. And what I want to do is I want to fit that up to an equation, to a model. Okay, so I say, well, I fit it up to the model, the GXS is x1, x2 times omega. And I find that if I try to fit that over the entire range from here to here, my fit isn't perfect. I need to add an additional term. I need two terms. Okay, so let's use two terms. So let's say x1, x2, a plus bx2, where a and b are temperature independent. Okay, now I get a nice fit. Or would there be another way of doing it? I can say GXS is x1, x2. Here I have a and b are not functions of temperature, but they're functions of, when I just had the omega is independent of t and x, and that isn't quite enough. I need a second term. So here I can add a second composition term, making these independent of composition, of temperature. So what does that mean? What that means is that, so a does not equal a function of t, b does not equal a function of t. Remember that GXS is equal to delta H minus TSXS. So by not making this a function of t, what I'm really assuming here is I'm assuming that SXS equals 0. And I'm putting the extra term, I'm putting it into the delta H term. Remember, the strictly regular solution with x1, x2 omega, that's all enthalpy. Okay, but there's another way to do it, to add a second term. I could add GXS equals x1, x2, omega minus a to t, where omega and eta are composition independent. And now I'm putting the variation in temperature. And I'll probably get a good fit with this and a good fit with this. Okay? But they're different. In this case, this is SXS and this is delta H. It's not a function of composition, and this is not a function of composition. So here I'm assuming a constant H and SXS independent of composition, but they vary with, SXS is not 0. So GXS varies with T, but not with composition. GXS over x1, x2 varies with T, but not this way. Now, both cases are going to give you a good fit. You probably get just as nice a fit to the liquidus either way, but you're not going to get the same heat and entropy. So you're getting G, all the liquidus gives you is GXS. It doesn't give you H and SXS independently. And you can make this assumption or you can make this assumption, but this is based upon either other experimental information or upon your concept of what's probably more correct in this particular case. And why is this important? If all you're trying to do is fit the binary phase diagram and reproduce the liquidus, it doesn't matter. But if you're now, say, trying to go from this system into a ternary system, then in the ternary system you may want to go down to other temperatures. Okay, in the ternary eutectic, and here the liquid phase only goes down to here. But in the ternary system, the liquid phase may go down another couple of hundred degrees to a ternary eutectic. And then you've got to extrapolate GXS down Now, if you extrapolate it this way, it's going to be very different than if you do it this way, because this way it changes with T, this way it doesn't change with T. But if you put this into your optimization program, and you do the calculation, you say, give me these two parameters, and FactSage will give you the two parameters, or you say, give me these two parameters, it'll give you those two parameters, you get a nice fit. But that doesn't mean it's the right fit. In something like gold silicon, the gold silicon system, this is most likely true, because the thing is so close. When things are close to ideal, generally, we'll talk about this later too, if the system is close to ideal, then this term tends to be bigger than this term. In other words, if you're going to assume that one term or the other is zero, you better to assume it's close to a random mixing, and the heat of mixing term is where the deviations tend to be. But that's just like experimental or experience, that isn't actual thermodynamics. So this is why I say it's nice to be able to write out these equations and think about what you're really getting. So here you're not getting H and S, you're getting a non-isothermal, you're getting a GXS along a path, which is not a constant temperature. Just to make one final little thing, this was gold silicon. This is a useful thing too. Suppose we do have a small solid solubility. Okay, small solid solubility. Now I'm going to write the same equation, RT log of the activity of silicon on the liquidus minus RT log activity of silicon on the solidus equals minus the Gibbs energy of fusion of silicon. All right, let's say, we know the system, I'm going to make again, you have to make some assumptions, but let's say the liquid is ideal and the solid is Henrian. So we're saying we have a close to ideal, or let's not even assume the liquid is ideal. Let's say the liquid thermodynamics is known. We know the thermodynamic properties of the liquid from some other measurements, the activity measurements or something. Okay, so then on the liquidus I can calculate at any point on the liquidus I have any composition here. I know this composition. I know the liquidus. Liquidus thermodynamics are known, and the liquidus is known. Known means measured. Okay, liquid thermodynamics is known. That is, gamma silicon is known as a function of composition and temperature. Okay, so that is, I have the phase diagram, so I know I have a liquidus here, and I know the activity coefficient of silicon at that liquidus point. Okay, so what I can write is RT log mole fraction of silicon on the liquidus plus RT log gamma of silicon on the liquidus plus minus RT log activity of silicon on the solidus equals minus the Gibbs energy of fusion. Okay. Same thing. Now I assume that the liquidus composition is phase diagram is known, so the liquidus composition is known. The thermodynamic properties of the liquid are known. They measure the heat of mixing, they measure the activity somehow. So this entire term is known at any given temperature. The solid is a dilute solution. Okay, the solid is a dilute solution. It's Henrian. So you have a Henrian, it's Henrian for the solvent, that is the gamma naught of gamma of gold is approximately a constant, gamma Henry of gold, and then it's Rayleighian for the solvent, silicon. So that means that the activity of silicon, solid, is approximately equal to the mole fraction of silicon in the solid, provided that this is a dilute solution. So the mole fraction of silicon on the solid is like 0.99, 0.98, 0.97. Okay, so if you know that, then you make this in here, so this becomes the mole fraction of silicon in the solid, and so now I can calculate the mole fraction of silicon in the solidus. Okay, I know the thermodynamic properties of the liquid, so I know the mole fraction. at the liquidus, I know when I know what X silicon is 0.81, I know the temperature is 1523, so I put in 1523, I put in 0.81, and the activity coefficient of silicon in the liquid is known at that point, or I might assume it's ideal. And then I can solve this equation to give me the activity of silicon in the solidus, on the solidus, but if the solid is pretty close to being a Reoltian solution for the solvent, which is always the case if you have a dilute solution, this is going to be pretty close to the mole fraction of silicon solid. So this would give me an approximate estimation of what the mole fraction of silicon in the solid is. Now this is not a really accurate way of doing it, but I mean if I calculate 0.98 here, then I mean that's probably, it could be 1, it could be pure. But if I calculate like 0.85 or something, then clearly it's nowhere near. Okay, so this gives you a rough idea of what's going on. And this is not, I've done this quite frequently sometimes. So in other words, this also comes back to, I can calculate the liquid, you can calculate the liquidus, assuming no solid solubility, and see how close that comes to the liquidus with solid solubility. So I might give you a... Okay, so as the solid solubility increases, that also pushes the liquidus up. As this equation just becomes less than 1, this has to go the other way. So if you have solid solubility, if you have no solid solubility, that gives you the lowest possible liquidus. The more solid solubility you have, the solid solubility pushes up the liquidus. Okay, so this is kind of a useful calculation which you can do very quickly sometimes just to see if the solid solubility, order of magnitude idea of the solid solubility. This is not going to give it to you exactly, but certainly 0.99 will be different from 0.85 or something. You can find out pretty quickly whether it's a good assumption or not. And maybe even that the eutectic would be even more. Okay, and a final thing that's going way ahead, but while we're here. Okay, in order to do this then, in order to get the mole fraction of silicon, the solidus, along the solidus line, you'd have to know the thermodynamic properties of the liquid phase. Okay? So in other words, you'd have to know the mole fraction of silicon. Suppose, however, that you're very, very close, you're up here. We're talking about the liquidus at like 99–98% silicon. In that case, the liquid phase 2 is Reoltian, because you know Reolt's law, as any phase approaches the pure solvent, the activity approaches 1. Okay, so if I'm in the limiting region, if I'm at this liquidus lie in the first 2–3%, okay, I don't have to know the thermodynamic properties of the liquid, because I can assume that the liquid is ideal. In that case, I can assume both the solid and liquid are ideal. And it doesn't matter, it's not an assumption. Both, the liquid doesn't have to be ideal, but as you approach pure silicon, the liquid phase and the solid phase become ideal. So therefore, in the limit, as X silicon is approximately equal to 1, I can write RT log of X silicon in the liquid minus RT log of X silicon in the solid equals minus the Gibbs energy of fusion of silicon. Okay, and even this now I can make the delta Cp as 0, because this really is, you're very close, this then really is approximately equal to minus the heat of fusion times 1 minus T over T fusion. That was an approximate equation assuming Cp solid equals Cp liquid, but over a few degrees it's going to be damn close to that. Okay, and so now I can find out if there's solid solubility very quickly. I assume no solid solubility. So this term goes to 0. And calculate the liquidus, assuming ideal. Now, this has to go into the true liquid. The true liquidus has to come in with that limiting slope. And calculate. This could be your real liquidus, and this could be your ideal liquidus. But the ideal liquidus and the real liquidus come in at the melting point with the same slope. Okay, so all that really matters is the limiting slope of the liquidus. You have your measured liquidus, you get the limiting slope like this, and see if the limiting slope agrees with with this equation. If it does, then that shows that you have very small solid solubility. If the limiting slope is higher, then you do have some solid solubility, and you can even calculate the ratio of X silicon liquid to X silicon solid. If you find that your ideal limiting slope is below the measured limiting slope, then you know the phase diagram's wrong. Okay, because you can't go lower. And this is a test that should be done with every phase diagram. It just only takes you a couple of seconds with your down calculator. As you calculate, when you see a measured phase diagram, calculate the limiting slope from this equation. Make that for no solid solubility. Make that equal to 1, calculate your limiting slope, and see if it agrees. And if it's way, way higher, then you probably have solid solubility, or maybe there's something wrong with the phase diagram, but it's certainly the zero solid solubility line is calculated, and it's only calculated from the heat of fusion and the melting point. You don't need any other information to get it. Okay, so you get a lot of information just by looking at those two limiting slopes. I'll give you a better equation for it in the future. Kind of clear what I'm doing?
Just to verify, I don't see any effect of the gold in the limit of. Does it mean that for all binary diagram, all the slope will be the same on the silicon side?
Yeah, provided it's silicon, because the only thing that it would be the same, no matter what your solute was.
Yeah.
This could be gold, silver, tin, whatever. As long as there's no solid solubility, it's the same limiting slope, because all the liquid has become ideal in the limit. So you get the same limiting slope. And I will give you an example, homework example. This is a method actually of getting the heat of fusion. Say you have a really high melting point. It's really hard to measure a heat of fusion calorimetrically when it's 3,000 degrees. But if you know that there's no solid solubility, you take a solvent, silicon, you put something in it where you know there's no solid solubility. This is usually pretty easy. You take something that isn't at all like silicon chemically. You know it's not going to dissolve in the solid. And then you do a few little liquidus measurements, thermal analysis measurements over a range of 10, 15 to 10 degrees or so from the melting point. And from the limiting slope, this equation, you can find out what the heat of fusion is. That's a good way of getting heat of fusion. It's much easier to do a thermal analysis to measure a few liquidus points than it is to measure a heat of fusion in a calorimeter at 2,000 degrees.
Is it also applied in metal compound?
Yeah, but into what? To intermetallic? No. Because in an intermetallic compound, you mean like when you have a... Well, remember, this is really a maximum in a two-phase region, right? And the limiting slope is 0. It doesn't come up like this, it comes around like that. It might look very much like it comes up strong, but it really doesn't. It's really so your limiting slope is not. The limiting slope is always 0, theoretically. If your limiting slope comes up, well, I won't get into that now. That depends upon, for really highly ordered liquids, you're pretty close. But that's because the liquid is almost like a one component. In other words, if I were to draw the sodium chlorine phase diagram, then your compound would be, to all intents and purposes, a peak like this, and this would be the sodium chloride diagram, and you could do the limiting slope. And that's only because the liquid is an ordered NaCl liquid. It's quasi-one. But that has to do more with the modeling than anything. But in principle, no, you can't. It only applies to the pure. Way back when I was a master's student doing some experimental work, I actually did some thermal analysis, and I measured a a binary phase diagram. Um, and I found that the heat of fusion, I used the heat of fusion that I got from the literature and used that, and I found my limiting slope agreed quite nicely and all that. But then I went back to the literature, and the heat of fusion that was in the literature had actually been determined by measuring the phase diagram and taking the limiting slope, you see, so naturally it worked perfectly. Yeah, I went into the phase diagram for Sarama's book, and I found that these phase diagrams just were beautiful because the limiting slope was exactly what you predicted from the heat of fusion, and everything was fine. And this showed absolutely no solid solubility, and I did this analysis, and when I found the people who got the heat of fusion had used this technique. So that proved nothing. Actually, quite a few, I think, especially high melting measurements, high melting metals and so on. This is the way that's actually done. But this, so it doesn't matter, and that's the way to check it then. Again, the other way to check it, I want to get the heat of fusion of silicon. I'm not sure whether gold has zero solid solubility or not. Well, okay, do it with gold, do it with 2 or 3 other metals, and as you said, it should be totally independent of the solute. If it isn't independent of the solute, then at least one of them has got solid solubility. But if you do 3 or 4 solutes and they're all gives you exactly the same limiting liquidus, then you're pretty certain that you've got the same. Okay, so this is kind of the advantage of doing things that way. All right, I wanted to go a little further today, but hell, this is like I think a good place to stop. Because, okay, okay, for homework. Okay, the material for we set a quiz in 2 weeks on Wednesday the 19th, that's okay, test. Wednesday the 19th, we'll work out the timing later on. Okay. The material for the quiz is up to this point here. Okay, what I talk about next week won't be on the quiz, that's different. And the homework problems include the homework problems I'm giving you today. Next week I might give you some review homework problems if you want to use them that review the same material, the materials up to this point, including today's homework problems. Before I give you the homework problems, I'd like you to read section 6. The whole thing. Section 6 is on ternary phase diagrams in here. I am not going to go over this in class. It's some of the thermodynamics. It's mainly just how to interpret standard. This is the standard temperature composition diagrams, isothermal sections of ternary systems, and so on. Be sure you understand it. So what you read it, I know the author. It's extremely clear. And but if you have questions about it, you could ask them next week, and I can ask you. So read section 6 on ternary phase diagrams, and if you have any questions next week, I can answer them in class. You might also want to read sections 8.1. That's fairly short. I will probably get to talk about that next week as well. For the devoir, all the homework problems, all based on what I talked about here, the RT log activity, liquid minus RT. That's the equations you want for these devoir. And that is section 13, numbers 18, 3, 4, 11, 15, 12, and 32. Now there is another one, I think this is, this written down there. Number 18, question 17. Okay, these here use what I did here, the RT log liquid. This 18, number 17, is an application of the phase rule that I talked about on Tuesday. maybe we could look at 1817. Number 17, all right. Okay, so during the, I just want to reword, this is the phase rule. During the production of copper, you suppose you have a production of copper, so we're going to have here a matte phase which contains copper, iron, sulfur, and oxygen. That's your matte phase, is mainly copper iron sulfide with some oxygen. You have a slag phase. The slag phase contains silica, it's going to contain FeO, it's going to contain Fe2O3, it's going to contain copper, and it's going to contain sulfur dissolved in there. Everything's going to be dissolved in there. And up here you're going to have a gas phase, which is going to have oxygen, nitrogen, SO2, SO3, and a whole bunch of other stuff in the gas phase. And we assume the three phases are in equilibrium. Okay, so you suppose it's in equilibrium with the temperature is constant, so we have T equals constant, we have P total equals constant. The temperature is constant, the pressure is constant, equal to 1 atmosphere. I worded the question this way, you could word it another way. Maybe this is not the right way to word it. All the thermodynamic properties, equilibrium constant activities, all the thermodynamic properties are known of the phases, so you can do a complete thermodynamic analysis of the system. An engineer says that, at least in principle, he can calculate the composition of the matte phase using the thermodynamics as long as he makes some measurements. He says that all he has to do is he has to measure, if he measures the partial pressure of SO2, he measures the partial pressure of oxygen, and he measures the copper content of the slag. So he's going to measure PSO2, he's going to measure PO2, and he's going to measure the sulfur content of the slag, weight percent sulfur in the slag, and then knowing the temperature and pressure too, of course. He can then calculate, in principle, if he had all the thermodynamic properties, he could calculate exactly the composition of the matte phase. Okay, another way of putting it would be the following. Supposing I have, let's say I have two systems. I have two systems here. Okay, and these two systems have the same temperature, the same pressure, the same PSO2, the same PO2, and the same sulfur content of the slag. Then the same thing would be saying that then according to the phase rule, they're exactly the same. All the phases have the same composition. Not necessarily the same amounts. And the phase rule doesn't give you the total amount. You could have one system, you could have two systems. One system could have like a lot of slag and very little matte. The other system could have very little matte and lots of, and so on. But the compositions would be the same. Okay, it's not possible to have two systems with same SO2, same O2, same T and P, and the same sulfur content of the slag, unless all other compositions are identical in terms of everything. Is that true or is that not true? Okay, so apply the phase rule, we'll tell you that sort of thing. And this thing can be useful sometimes because you know then how many things are determined by the system, or similarly, if two systems differed slightly in iron content of the slag, could they have the same, how many variables are actually independent variables? How many things can change here? So that's the other way of looking at it. It means the same thing. Now, it doesn't mean the two systems are exactly identical in terms of the amount, but they're identical in terms of the composition. Remember when I talked about the phase rule, I said there are phase rule variables. Temperature, pressure, chemical composition of each phase, not total composition, but phase compositions. and so on. These are your variables. Okay, so if your degrees of freedom is 0, then all the phase diagram variables have to be the same everywhere. But the total amount of each phase is not a phase diagram variable. Okay, so PSO2, PO2, weight percent sulfur in the slag, temperature and total pressure, is that enough to completely define the system? In other words, is the number of degrees of freedom 0? Okay, I'm going to give you one final homework problem. I'm going to show you how this works. I didn't show you this before. If you go to the website, you will find something on here called what? Why is it not here? Oh, here we go, old exams. Should be old exams. Yeah, old exams, I think is it. No, old exams, number 30. Yeah, so these are some of the old exams from this course in past years. In general, I had a control 1, control 2, and final exam. Okay, you're now doing control 1, so this would be control 2. Yeah, also each year the material was a bit different, and certainly the order was a bit different, so don't panic if you can't answer all the questions. I can give you some of these too next week. But do the old exams. So if you go down here, this is number 30, and I wanted you to do 2003 final exam question 2. So here you scroll down to, so here's 2003 final exam question 2. Okay, so that's a big point. So we have exam 2003, examen final number 2. So next week I'm going to, well, I'll take up these, and then I'll also, if you have any questions on the section 6 on ternary phase diagrams, ask them. Next week I will assign again some other review problems that you can work on some more for the test. And for the material next week I'll be starting, really be starting thermodynamic modeling, so I'm going to start. We had the regular solution, and now we're going to start talking about general polynomial expansions, Kohler, Mugiano interpolation techniques, and examples of optimization using polynomial equations, the standard CalFAT technique. And that should take next week, and then after that we'll start probably the following week, get more into the more advanced solution models involving short and long range ordering and different kinds of solutions. I've done the order a bit different this year. I've really tried at the beginning to give them all the basic thermodynamics, phase diagrams, the whole basic stuff all at the beginning, and then the models will come now. Other years I've kind of interspersed them a bit, but I thought maybe this is a better way to get the whole, all the fundamental thermo. So you've seen all the fundamental thermo that I can give you. And it's been very quick, so I hope you're not... Do you have any questions about the exam or what? Sorry? Oh, the exam. Okay, first of all, the exam is open book. You can bring all the material you want. Okay, that's...
Wednesday morning?
when would you prefer it?
Because in the afternoon we have research. So
It's totally up to you when you'd like to have it. I'd like to give, I don't like them to be a big rush to answer the questions as quickly as you can, so I like to give everybody maybe 3-4 hours to do it. I do have a time limit. I mean, you can't sing around here all day, but you know, I'll set the time limit to be very generous, 3.5 hours, and then you should be done after 2.5 anyway, but if you're not, you can so you should give yourself enough time if you need. So in that case, you could start earlier in the morning if you want. Generally, we come here and we put people around different rooms. Or you can discuss it and let me know next week what time. Anytime on Wednesday the 19th is fine with me, but give yourself 3.5 hours so that we have enough time. Okay. Ready, 1, 2, 3, go.